Imagine an enormous, invisible shell that envelops our solar system from the very edge of its boundaries and stretches far into the vastness of interstellar space. This colossal structure, known as the Oort Cloud, is believed to be composed of billions, or even trillions, of ancient icy chunks. Each of these chunks is not merely a small piece of rock or ice, but can be comparable in size to the great mountains found on Earth. These icy fragments are remnants from the early days of our solar system, having formed over 4.6 billion years ago when the Sun and its surrounding planets were just beginning to coalesce from a swirling disk of gas and dust. As a shell, the Oort Cloud is thought to encircle the entire solar system, forming a vast spherical boundary that marks the transition from the dominion of our Sun's influence to the uncharted territories of interstellar space. Despite its immense scale, the Oort Cloud remains hidden from direct observation, primarily because these icy bodies do not emit their own light and are located at extreme distances from the Sun. Their presence is inferred through the study of long-period comets, which occasionally send fragments hurtling into the inner solar system. The sheer size and scope of the Oort Cloud are staggering to contemplate. It represents not only the outer limits of our solar system, but also a repository of the primordial building blocks that once formed the planets. The structure's formation and existence provide crucial insights into the history and evolution of our cosmic neighborhood. Even though we have yet to directly observe this immense icy barrier, its theoretical presence continues to intrigue astronomers and fuels ongoing debates about the true scale and nature of our solar system's outskirts. Its enigmatic existence challenges our understanding of space indeed. The Oort Cloud is often compared to two other well-known structures within our solar system: the asteroid belt and the Kuiper Belt. While all three represent regions filled with remnants from the early solar system, their characteristics differ dramatically in terms of location, shape, composition, and scale. The asteroid belt is the region that lies between Mars and Jupiter, spanning roughly from 2 to 3.5 astronomical units, (Sun AU), from the Sun. This belt is a relatively narrow band of rocky debris and metal fragments, millions of small bodies that never coalesced into a full-sized planet due to the strong gravitational influence of nearby Jupiter. The objects in the asteroid belt are generally rocky and metallic, and because they orbit relatively close to the Sun, they are bathed in sunlight, which makes them easier to observe with telescopes. Their orbits tend to lie within a common plane, the ecliptic, which is the same plane in which the major planets orbit. In contrast, the Kuiper Belt is located much farther out, extending roughly from 30 astronomical units to about 50 astronomical units from the Sun. This region is a vast, donut-shaped ring that exists beyond the orbit of Neptune. Unlike the rocky asteroids of the inner solar system, the Kuiper Belt objects, KBOs, are composed largely of ices, water, methane, ammonia, and other volatile compounds. This belt is home to many dwarf planets, including Pluto, and serves as the source region for many short-period comets. The Kuiper Belt's objects share a similar orbital plane, much like the asteroid belt, and their relatively close proximity compared to the hypothesized Oort Cloud allows us to observe many of these bodies directly. Now, imagine a structure that takes the concept of a debris field to an entirely different scale and geometry. The Oort Cloud. Unlike the asteroid belt and the Kuiper Belt, which both lie in relatively flat, disk-like regions, the Oort Cloud is believed to form a vast spherical shell around our solar system. This spherical arrangement means that the objects within the Oort Cloud are distributed in all directions, not just confined to the ecliptic plane. The inner boundary of the Oort cloud is thought to begin at a distance of roughly 2,000 to 5,000 astronomical units from the Sun, while its outer edge might stretch as far as 100,000 astronomical units or even more. To put this in perspective, 1 astronomical unit, the distance from the Earth to the Sun, is about 150 million kilometers. Thus, the Oort cloud would extend an immense distance, marking the outermost reaches of our Sun's gravitational influence. The scale of the Oort cloud is staggering when compared to the asteroid and Kuiper belts. Whereas the asteroid belt occupies a narrow band relatively close to the Sun, and the Kuiper belt extends only a few dozen astronomical units farther out, the Oort cloud is a repository of icy bodies that extends thousands of times farther. Its spherical nature suggests that, unlike the more structured and predictable orbits of the inner solar system, the objects in the Oort cloud follow paths that are highly varied in direction and inclination. This randomness is a result of the gravitational scattering that occurred during the early formation of the solar system. As the young Sun and the newly formed giant planets began to clear out the remnants of the solar nebula, many small icy bodies were ejected into distant eccentric orbits, eventually forming the diffuse halo that we now refer to as the Oort cloud. Another critical difference between these regions lies in their physical properties. The objects in the asteroid belt are primarily rocky remnants, chunks of material that never fully merged into a planet. The Kuiper belt, on the other hand, contains a mix of rock and volatile ices, which is why many of its members are classified as icy bodies or dwarf planets. In the case of the Oort cloud, the bodies are presumed to be even more primitive and icy, largely untouched by the warming influence of the Sun. Due to their vast distance, these objects remain in a frozen state, preserving materials from the early solar system that could offer clues about the conditions present during the time of planetary formation. Furthermore, the method by which we observe these regions differs significantly. The relatively close proximity of the asteroid belt and the Kuiper belt allows astronomers to study their objects using reflected sunlight. Telescopes, both ground-based and in space, can capture images and spectra of these bodies, providing valuable information about their composition and dynamics. In stark contrast, the Oort cloud is so remote that its icy objects do not reflect enough sunlight to be detected by even the most powerful telescopes currently in operation. Instead, the existence of the Oort cloud is inferred indirectly through the behavior of long-period comets. These comets, with orbital periods stretching over thousands or even millions of years, appear to originate from a spherical distribution around the solar system, strongly suggesting the presence of a vast reservoir of icy debris at extreme distances. The differences in structure also have profound implications for the formation and evolution of our solar system. The flat, disc-like configurations of the asteroid belt and Kuiper belt are consistent with the theory of planetary formation, where the material in the protoplanetary disk gradually coalesced into larger bodies under the influence of gravity and rotational dynamics. The Oort cloud, however, represents a more chaotic and less understood aspect of solar system evolution. It is thought to be the result of early gravitational interactions that flung material outward, where it became loosely bound to the Sun. The fact that this material now forms a spherical halo rather than a flat disk tells us that the early solar system experienced significant dynamical upheaval, processes that are still a topic of active research and debate among astronomers. Moreover, understanding the differences between these three regions is crucial for piecing together the history of our solar system. The asteroid belt gives us a window into the rocky inner regions where terrestrial planets like Earth formed, while the Kuiper Belt offers insights into the outer, colder regions where ice played a major role in the accretion process. The Oort Cloud, meanwhile, holds the potential to unlock secrets about the very limits of the Sun's reach and the processes that govern the outermost boundaries of our gravitational neighborhood. Its existence, inferred through the study of cometary orbits and supported by complex mathematical models, challenges us to expand our understanding of what constitutes the solar system. It underscores the idea that our solar system is not confined to the neatly ordered paths of the inner planets and their nearby neighbors, but instead extends into a vast and largely uncharted frontier of icy bodies and distant mysteries. In summary, while the asteroid belt and Kuiper Belt are more easily observable and exhibit a relatively organized disk-like structure, the Oort Cloud stands apart as a sprawling, spherical shell that reaches unimaginably far into space. This stark difference in scale and structure not only highlights the diversity of the solar system's remnants, but also deepens our appreciation for the dynamic and sometimes chaotic processes that have shaped our cosmic neighborhood over billions of years. The evidence for the existence of the Oort Cloud is rooted in the study of long-period comets, celestial travelers whose enigmatic journeys have provided astronomers with crucial clues about the farthest reaches of our solar system. In this discussion, we delve into how observations of these comets, particularly the clustering of their aphelia at vast distances from the Sun, led to the hypothesis that a massive spherical reservoir of icy debris surrounds our Sun. Long-period comets, messengers from the outer solar system. Long-period comets are characterized by their extraordinarily elongated orbits, with periods that can span tens of thousands to even millions of years. Unlike short-period comets, which typically originate from the relatively nearby disk-shaped Kuiper Belt, long-period comets display a far less predictable behavior. Their orbits are not confined to the narrow plane of the solar system. Instead, they approach from virtually every direction. This randomness in orbital inclination, along with the enormous distances these comets travel before swinging back toward the inner solar system, immediately suggested to astronomers that their source was not a structured flat region like the Kuiper Belt. One key aspect that caught the attention of early researchers was the aphelion of these comets, the point in their orbit where they are farthest from the Sun. Detailed observations showed that many long-period comets reached their aphelia at distances clustering around a certain value, roughly 50,000 astronomical units, AU. An astronomical unit, which is the average distance between the Earth and the Sun, about 150 million kilometers, serves as a convenient yardstick for measuring cosmic distances. The clustering of comet aphelia around such a vast distance indicated that these icy wanderers likely originated from a specific, distant reservoir of material that had been perturbed and set on highly eccentric paths. This striking observation led Dutch astronomer Jan Oort, among others, to propose that a spherical cloud of icy bodies, later dubbed the Oort Cloud, must exist as a gravitationally bound reservoir far beyond the Kuiper Belt. According to Oort's theory, during the early formation of the solar system, a swarm of planetesimals, the building blocks of planets, remained after the major planets had formed. The nascent giant planets, with their substantial gravitational pulls, scattered many of these remnants outward. Some of these icy bodies were flung so far away that they eventually settled into long, loosely bound orbits around the Sun. Over billions of years, this collection of icy debris coalesced into what we now refer to as the Oort Cloud, a vast spherical shell that serves as the source of long-period comets. The fact that these comets come from all directions is a significant piece of evidence. If the debris were confined to a disk, as with the asteroid belt or Kuiper Belt, we would expect a more uniform and planar distribution of cometary orbits. Instead, the nearly isotropic, directionally uniform distribution of long-period comets strongly supports the idea that they originate from a spherical envelope of material, a structure that completely surrounds our solar system in all directions. Further support for the Oort Cloud hypothesis comes from detailed mathematical modeling and computer simulations of the solar system's early dynamics. These models take into account the gravitational interactions between the early Sun, its giant planets, and the myriad of planetesimals present during the system's formation. They show that the chaotic gravitational interactions during that formative period were indeed capable of ejecting a large fraction of these icy bodies into distant orbits. Over time, these bodies would have settled into the vast, diffuse cloud observed indirectly today. The aphelion clustering at approximately 50,000 astronomical units is particularly telling. It suggests that the gravitational influence of the Sun extends much farther than the orbits of the known planets, or even the Kuiper Belt objects. Once an icy body reaches these remote distances, its orbit is only weakly bound to the Sun. This makes the Oort Cloud a dynamic reservoir, where even minor gravitational disturbances, such as those from passing stars, molecular clouds, or tidal forces from the Milky Way, can nudge objects onto trajectories that send them hurtling back into the inner solar system as long-period comets. The study of long-period comets not only bolsters the case for the Oort Cloud, but also provides a unique window into the conditions that prevailed during the early history of our solar system. These comets are essentially time capsules, preserving primordial materials that have remained relatively unchanged for billions of years. Their compositions can offer insights into the temperature, pressure, and chemical makeup of the solar nebula, the cloud of gas and dust from which the Sun and planets formed. When a long-period comet finally enters the inner solar system, it often develops a glowing coma and tail as the Sun's heat sublimates its icy components. By analyzing the light emitted and absorbed by these comets, astronomers can determine the presence of various volatile compounds, such as water, carbon monoxide, and methane. The fact that many of these compounds exist in higher concentrations than expected from objects formed closer to the Sun provides further evidence that long-period comets originated from an extremely cold, distant environment, a region that corresponds well with the predicted location of the Oort Cloud. Despite the compelling indirect evidence, the Oort Cloud itself remains elusive to direct observation. The icy bodies that comprise it are tiny and extremely far from the Sun, making them too faint to be seen with even the most advanced telescopes available today. Their lack of intrinsic luminosity means that, unlike stars or even the larger bodies in the asteroid and Kuiper belts, they do not emit or reflect enough light for direct detection. This observational challenge has led astronomers to rely on the study of comets that venture into the inner solar system as the primary method of inferring the existence of the Oort Cloud. Advancements in technology and observational techniques continue to refine our understanding of these distant regions. Space missions, improved telescopic instrumentation, and more sophisticated computer models all contribute to a more nuanced picture of how the Oort Cloud might be structured and how it interacts with other components of the solar system. Nonetheless, the very nature of the Oort Cloud, as a diffuse, remote reservoir of ancient icy debris, ensures that much of its mystery remains intact, waiting for future discoveries to shed light on its true nature. Another intriguing aspect of the Oort cloud hypothesis is the dynamic interplay between the cloud and the rest of the galaxy. Over vast spans of time, the orbits of Oort cloud objects can be altered by gravitational interactions not only within the solar system but also with external forces. Such events might explain why we observe an influx of long-period comets at irregular intervals, a direct consequence of the ever-changing gravitational landscape of our cosmic neighborhood. This dynamic behavior is critical for understanding the long-term evolution of the solar system. The exchange of material between the Oort cloud and interstellar space could have implications for the chemical enrichment of both the solar system and the galaxy. Moreover, studying how these distant objects respond to gravitational disturbances provides valuable data for testing and refining our models of solar system dynamics. In essence, the long-period comets serve as both messengers from the deep past and active participants in the ongoing evolution of our celestial environment. The objects populating the Oort cloud are only weakly bound to the Sun's gravitational field due to the enormous distances involved. When a star passes relatively close to our solar system, its gravitational field can disturb the orbits of the Oort cloud objects. Even a low-mass star, if it ventures near enough, can impart enough force to alter the trajectory of these distant bodies. Molecular clouds. These massive concentrations of gas and dust move through the galaxy. As one of these clouds passes by, its collective gravitational influence can act similarly to that of a passing star, gently nudging objects in the Oort cloud. Galactic tidal forces. The Milky Way itself exerts tidal forces on our solar system. Over long periods, the gravitational field of the galaxy can slowly reshape the orbits of objects in the outer regions of the solar system, contributing to the overall dynamism of the Oort cloud. In each case, these gravitational perturbations alter the energy and angular momentum of the objects in the Oort cloud. In many instances, the result is a change in the eccentricity of an object's orbit, transforming a previously stable, near-circular path into a highly elliptical trajectory that brings the object closer to the Sun. Among the various external forces, passing stars are considered one of the most significant triggers of orbital change within the Oort cloud. Due to the sparse distribution of stars in the solar neighborhood, close encounters are rare on human timescales. Yet over billions of years, such encounters accumulate. When a star passes through the outer regions of the Oort cloud, its gravitational field can act like a cosmic cue, dislodging objects from their long-term orbits. These dislodged objects then become candidates for becoming long-period comets. If the gravitational pull from the star is strong enough, it can decrease the orbital energy of some objects, effectively pulling them into orbits that extend closer to the Sun. This process not only helps explain the sporadic appearance of long-period comets in our inner solar system, but also illustrates the interconnectedness of our solar system with its galactic environment. A particularly intriguing example of a passing star influencing the Oort cloud is provided by Schultz's star. Approximately 70,000 years ago, this low-mass binary star system, comprising a red dwarf and a brown dwarf companion, made a relatively close approach to our solar system. Although its gravitational influence was much weaker than that of our Sun, the close encounter allowed Schultz's star to graze the outer regions of the Oort cloud. During this brief encounter, the gravitational perturbation from Schultz's star was sufficient to nudge some of the icy objects in the cloud, altering their trajectories. Numerical simulations conducted as recently as 2018 suggest that such encounters, even when involving relatively low-mass stars, can lead to noticeable changes in the orbits of Oort cloud objects. The result is that a fraction of these objects are sent on long elliptical paths that eventually bring them into the inner solar system as comets. The case of Schultz's star is significant because it underscores that even seemingly minor gravitational interactions can have long-term consequences. Over the 4.6 billion-year history of the solar system, countless such encounters have likely occurred. Each interaction contributes incrementally to the continuous reshaping of the Oort cloud, ensuring that it remains a dynamic and ever-evolving structure. Researchers have employed sophisticated numerical simulations to model the effects of gravitational perturbations on the Oort cloud. These simulations take into account the complex gravitational interactions between the Sun. The results from these models consistently indicate that the Oort cloud is not a static, isolated reservoir. Rather, it is a dynamic system where objects are constantly being perturbed from their original orbits. The simulations show that over long timescales, the cumulative effect of these gravitational nudges can lead to significant reshaping of the cloud's structure. The influence of gravitational perturbations on the Oort cloud is not a one-time event, but an ongoing process that has implications for the long-term evolution of the solar system. As stars and molecular clouds pass by, the orbits of Oort cloud objects are continuously modified. Over millions and billions of years, these incremental changes accumulate, leading to a slow but steady evolution of the cloud's structure. Additionally, these interactions have implications for the frequency of cometary activity within the inner solar system. The sporadic appearance of long-period comets, driven by gravitational perturbations, means that the rate of cometary influx can vary significantly over time. Periods of increased activity may correlate with epochs when the solar system experienced a particularly close stellar encounter, while quieter periods may follow in the absence of such disturbances. Implications for understanding the solar system. The role of gravitational perturbations in shaping the Oort cloud offers valuable insights into the dynamic history of our solar system. By studying the trajectories of long-period comets and modeling the effects of external gravitational forces, astronomers can reconstruct the past interactions that have sculpted the outer regions of our solar system. Moreover, the study of these perturbations has broader implications for our understanding of galactic dynamics. The solar system is not an isolated island in space. It is deeply embedded within the gravitational fabric of the Milky Way. The interactions between the solar system and the broader galactic environment are critical to understanding phenomena such as stellar encounters, the exchange of interstellar material, and even the potential triggers for mass extinction events on Earth. In this context, the Oort cloud serves as a natural laboratory for exploring the interplay between local and galactic-scale gravitational forces. In conclusion, gravitational perturbations from passing stars, molecular clouds, and the tidal forces of the Milky Way have a profound impact on the structure and dynamics of the Oort cloud. These external forces can alter the orbits of icy bodies residing in the cloud, nudging them onto trajectories that bring them into the inner solar system as long-period comets. The case of Schultz's star exemplifies how even low-mass stars can exert significant gravitational influence when they pass close to the outer edges of our solar system. Numerical simulations and theoretical models support the notion that the Oort cloud is a dynamic and ever-evolving reservoir of ancient material, a structure continuously shaped by the gravitational interplay with its cosmic environment. This ongoing process of gravitational interaction not only explains the sporadic appearance of long-period comets, but also highlights the intricate connections between our solar system and the broader galaxy. Over billions of years, the cumulative effects of these perturbations have sculpted the Oort cloud into the vast, diffuse shell we infer today. Moreover, the possibility of material exchange between the solar system and passing stars adds an intriguing layer to our understanding of cosmic evolution. Ultimately, the study of gravitational perturbations provides a window into the complex and dynamic processes that govern the outer reaches of our solar system. It reinforces the idea that even at the farthest distances, the solar system is not isolated, but is in constant dialogue with the rest of the galaxy. As technology and observational techniques continue to improve, future research may further unravel the mysteries of these gravitational interactions, offering deeper insights into the history and evolution of our cosmic neighborhood. Despite being a cornerstone in our understanding of the solar system's outermost reaches, the Oort cloud remains one of astronomy's most elusive and enigmatic structures. Unlike stars or galaxies that emit light and are easily captured by even modest telescopes, the Oort cloud's icy debris does not produce its own light and, due to its enormous distance from the Sun, reflects only a minuscule fraction of sunlight. This fundamental difference in brightness and proximity is at the heart of why we have yet to directly observe the Oort cloud, even though its existence is supported by robust indirect evidence and sophisticated mathematical models. The inner boundary of the Oort cloud is theorized to begin at around 2,000 to 3,000 astronomical units, AU, from the Sun. To put this in perspective, our nearest stellar neighbor, Proxima Centauri, is about 4.25 light-years away. In comparison, even the most distant planets in our solar system, such as Neptune, orbit at a mere 30 astronomical units from the Sun, and the Kuiper Belt extends only out to about 50 astronomical units. The Oort cloud's vast scale, therefore, makes any attempt at direct observation extraordinarily challenging. The objects within the Oort cloud are estimated to be roughly the size of a mountain. Imagine something akin to Mount Everest, which stands at about 9 kilometers tall. Telescopes can easily capture stars and galaxies billions of light-years away because those objects are either luminous by nature or emit vast amounts of energy across multiple wavelengths. In contrast, the icy remnants in the Oort cloud do not have such properties. They are inert, dark, and reflect only a whisper of sunlight, rendering them virtually invisible against the cosmic background. Given the inherent challenges of direct detection, astronomers have turned to indirect methods to infer the existence of the Oort cloud. Through careful observations and the application of advanced computer simulations, astronomers have been able to reconstruct the likely origins of these comets, and, by extension, the characteristics of the Oort cloud. Comparisons with other solar system structures. The difficulty in directly observing the Oort cloud becomes even more apparent when we compare it to other structures within the solar system, such as the asteroid belt and the Kuiper Belt. The asteroid belt, located between Mars and Jupiter, is relatively close to the Sun, typically between 2 and 3.5 astronomical units, and consists of rocky, reflective material that shines under solar illumination. Similarly, the Kuiper Belt, which lies beyond Neptune, approximately 30 to 50 astronomical units from the Sun, contains a mixture of rock and ice. Both these regions are within a range where the Sun's light is strong enough to make their objects detectable using modern telescopes. In stark contrast, the Oort cloud lies at distances that are tens of thousands of times greater than those of the asteroid belt or Kuiper Belt. As distance increases, the amount of sunlight available to illuminate an object diminishes dramatically, following an inverse square law. This means that even if the objects in the Oort cloud were as reflective as those closer in, their great distance would render them far too dim to be seen. It is, quite literally, a case of looking for a needle in a haystack. Except that in this instance, the needle is a small, dark mountain located in an incomprehensibly vast and dark haystack. The case of interstellar comets and alternative explanations. Adding to the complexity of the discussion is the observation of interstellar comets, such as Comet Borisov, first detected in 2019. Unlike typical long-period comets that are thought to originate from the Oort cloud, Comet Borisov exhibited characteristics, such as an unusually high concentration of carbon monoxide, that hinted at an interstellar origin. This discovery prompted some scientists to question whether all long-period comets necessarily come from our own solar system's Oort cloud, or if some might be interstellar interlopers. While the existence of interstellar comets adds an intriguing twist to the narrative, the overwhelming majority of evidence still supports the presence of the Oort cloud. The isotropic distribution of long-period comet orbits, the clustering of their aphelia, and the success of numerical simulations in replicating these patterns all point toward a vast, spherical reservoir of icy bodies bound to our Sun. Although the possibility of interstellar contributions cannot be entirely dismissed, they are considered exceptions rather than the norm. The balance of indirect evidence continues to favor the existence of a well-populated Oort cloud within our solar system. Historical context and the evolution of scientific thought. The inability to directly observe the Oort cloud has not deterred scientists from pursuing its study. In fact, history is replete with examples where indirect evidence led to monumental discoveries. During the 16th and 17th centuries, Copernicus and Galileo championed the heliocentric model of the solar system at a time when direct observational evidence was limited. Their groundbreaking work was based on careful observation of planetary motions and indirect clues, rather than on the direct detection of every celestial body. Over time, subsequent observations and technological advancements have confirmed their revolutionary ideas. Similarly, the case of the Oort cloud reminds us that in science, indirect evidence can be just as powerful as direct observation. Mathematical models and computer simulations provide compelling insights into phenomena that are beyond the reach of our current observational capabilities. They allow us to infer the presence and properties of structures, like the Oort cloud, even when we cannot see them with our telescopes. This process of building theories based on indirect evidence and then confirming them with new methods as technology advances is a hallmark of scientific progress. The promise of future discoveries. Looking ahead, the quest to directly observe the Oort cloud remains a tantalizing goal for astronomers. Future advancements in telescope technology, including instruments designed to detect extremely faint objects, may one day reveal the elusive icy bodies that make up this distant structure. Space missions that venture further into the outer reaches of the solar system could also provide valuable data, potentially capturing images or other forms of evidence that directly attest to the Oort cloud's existence. The challenge of detecting the Oort cloud also drives innovation in theoretical modeling and simulation. As computational power increases and our understanding of gravitational dynamics deepens, researchers can refine their models to better predict the behavior and distribution of Oort Cloud objects. These improved models will not only enhance our understanding of the Oort Cloud itself, but will also offer broader insights into the formation and evolution of planetary systems throughout the galaxy. The scientific value of an unseen structure. Even in the absence of direct observation, the Oort Cloud holds immense scientific value. It represents a repository of primordial material that has remained relatively unchanged since the formation of the solar system over 4.6 billion years ago. Studying the indirect evidence from long-period comets allows scientists to glean information about the conditions that prevailed during the early days of our solar system. In turn, this information can inform models of planetary formation and the chemical evolution of our cosmic neighborhood. Moreover, the concept of the Oort Cloud challenges our conventional notions of what constitutes the boundary of a solar system. It forces us to rethink the spatial limits of the Sun's influence, extending our understanding far beyond the orbits of the known planets. This has broader implications for astrophysics and cosmology, as it suggests that similar structures may exist around other stars, influencing the dynamics and evolution of planetary systems on a galactic scale. The intersection of observation, theory, and technology. The ongoing debate surrounding the direct observability of the Oort Cloud encapsulates the dynamic interplay between observational astronomy, theoretical modeling, and technological innovation. While current telescopic capabilities fall short of revealing the faint, distant objects of the Oort Cloud, advances in detector sensitivity, imaging techniques, and space-based observatories may one day bridge that gap. In the meantime, the strong indirect evidence provided by long-period comets and numerical simulations offers a robust framework for understanding this distant reservoir. This intersection of observation and theory is a testament to the iterative nature of scientific discovery. Each new observation, no matter how indirect, contributes to a more comprehensive picture of our solar system's structure. It reminds us that science often progresses not by what we can see, but by what we can infer from the subtle clues left behind by nature. Embracing the mystery. The inability to directly observe the Oort Cloud does not diminish its importance in our understanding of the solar system. Rather, it enhances its mystique and drives scientific inquiry. The vast distances, the minuscule light reflection, and the small size of its constituent objects combine to create a formidable observational challenge. Yet, through indirect evidence, most notably the study of long-period comets, and through rigorous theoretical modeling, astronomers have built a compelling case for the Oort Cloud's existence. In many ways, the story of the Oort Cloud is a microcosm of the scientific endeavor itself. A journey into the unknown, guided by clues, inference, and a relentless pursuit of knowledge. Just as Copernicus and Galileo reshaped our understanding of the cosmos without the benefit of modern technology, today's scientists continue to push the boundaries of what is known, even when direct observation remains out of reach. The Oort Cloud stands as a reminder that the universe is full of mysteries waiting to be unraveled, and that sometimes the absence of direct evidence can be as informative as its presence. As we look to the future, the possibility of directly observing the Oort Cloud may inspire new technologies and innovative missions that could one day confirm what our models and indirect observations have long suggested: that a vast icy shell indeed surrounds our solar system, silently preserving the ancient history of our cosmic origins. Thank you for watching.